Hello everyone and welcome to this presentation. My name is Jennifer Andersson and I will be presenting our IROS contribution titled Reinforcement Learning Control of a Forestry Crane Manipulator. This research has been carried out in collaboration between Umeå University and Algorithmic Simulation and constitutes the first successful implementation of a reinforcement learning controlled forestry machine. In particular, we're using deep reinforcement learning to automate the grasping motion of a forestry crane manipulator grasping logs in a simulated environment. We are also investigating the feasibility of using this approach to invoke energy efficiency in the grasping process. Alright, so let's begin with a first look. The results show that, using this approach, it's possible to learn successful actuator space control policies for energy-efficient log grasping using a simple curriculum in the learning process. Here you can see our best control policy in action, and during this presentation I will demonstrate further details, key points, and contributions of this research. Before we dig into the details of this approach, I will talk a little bit about challenges in the context of forestry automation. Many robotic manipulation tasks carried out in more controlled environments using small-scale manipulators have been mastered with traditional and intelligent control methods. Forestry machines, however, are heavy vehicles operating in very challenging and unstructured environments. The complex dynamics of the underactuated and kinematically redundant hydraulically actuated cranes add to the control complexity of these machines. This has contributed to the comparatively slow automation progress in forestry, despite the many automation incentives that exist, which include, for example, health perspectives of the human operators. To the left here, you can see an image of a human-operated forwarder. A forwarder is a vehicle equipped with a hydraulically actuated crane, tasked with loading and transporting logs from the felling site. As we can see, the forwarder is required to operate in challenging conditions, which include steep slopes and various lighting and weather conditions. So we quickly realized that full automation is a highly demanding task, but this research constitutes a starting point aiming to extend the application area of deep reinforcement learning control to heavy vehicles operating under similar conditions, and investigate the feasibility of using this approach to automate the grasping motion of forestry crane manipulators. To this end, we have made a few important initial delimitations, which I will go through now. Firstly, this work centers around the single log grasping motion from a non-moving vehicle. At this stage, we focus on the extracting, slewing, and grasping motion of the crane and grapple, and omit the part of the boom cycle in which the log is returned to the load bank. Secondly, we assume that the Cartesian position and orientation of the target log is known through, for example, an external perception system capable of providing this information in real time. Next, I will briefly go through the reinforcement learning framework, in which an agent navigates its environment and learns to achieve a goal through trial and error. In this framework, which is illustrated here, the agent observes the current state, and based on this observation, it chooses an action which then transforms the system into a new state. The agent then receives a reward based on some reward function designed to measure how well it's completing the goal. The goal of the agent is to maximize the total cumulative reward or expected return, and we want to find the optimal policy allowing the agent to take the optimal action in each state. The policy in this case is parameterized by a fully connected feed-forward neural network representing the distribution of actions given a state. The resulting policy approximator outputs a vector of actuator space motor control signals at each time step. We are using proximal policy optimization to optimize the policy, and this is an on-policy policy gradient method that has shown stable performance on a variety of tests in the past. Moreover, training is conducted using the Unity simulation platform together with the MLAgents toolkit and the physics engine AJX Dynamics. Our agent controls a 3D simulation model of a 6-wheel forwarder equipped with a kinematically redundant hydraulic manipulator controlled by 6 actuated degrees of freedom, which are marked in the sketch to the right. The position of the boom tip, where the end effector is attached, is determined by the rotational angles of 3 revolute joints and 1 linear displacement position. Starting from the base, a revolute joint, Q1, controls the slewing motion of the crane. The motions of the inner and outer booms are controlled by 2 actuated prismatic joints, Q2 and Q3, each representing a hydraulic cylinder. The telescope, Q4, can extend and retract along its axis and is controlled by a motorized prismatic joint. Finally, a revolute joint controls the orientation of the grapple along the rotator axis, and a prismatic joint controls the opening-closing motion of the grapple. This corresponds to 6 actuated degrees of freedom. Each actuated joint is equipped with a linear or rotational motor that is internally controlled to reach and hold a given target velocity, while obeying the current dynamics and constraints. 2 additional unactuated joints are also used, allowing the grapple to swing freely, which of course adds to the control complexity. So what does this mean for the observation and action spaces in our learning setup? The agent is controlled by action signals given to the velocity-controlled motors at each time step. The allowed velocity change per time step is limited, resulting in an essentially acceleration-based control system. The agent is able to observe its own state. So for each actuated joint, the agent observes the applied motor force or torque, the joint speed, as well as the joint position or angle. Moreover, it can observe the orientation and center of mass location of the target logs. As mentioned, the agent learns based on a reward signal. At the beginning of each episode, the grapple is placed above the load bunk, as can be seen here to the right, with the initial angle of each joint slightly perturbed. Logs are modeled as uniform cylinders, and the initial pose of the log is chosen randomly within a target area at the side of the load bunk. This is illustrated in blue at the ground level in the image to the right. For models without incentive for energy optimization, the agent is given a high sparse reward when the log is secured in the grapple, and the episode is terminated. To include an energy optimization goal, we simply scale this sparse reward signal inversely with the total energy consumed by the actuators up until the point of grasping, excluding the energy consumed by the grapple actuators, and assuming no energy recuperation. But we quickly encounter a problem using this reward structure, and it's related to the high dimensionality of the state space. If we use this reward structure, the agent explores indefinitely without ever attempting to grasp, so it can never learn. If we, on the other hand, use a continuous reward signal, for example based on the distance between the log and the grapple, the agent has learned to discard the grapple clause once it has finally learned to navigate to the log. But there is a quite simple and elegant solution to this problem. We propose a simple curriculum learning approach where we incrementally increase the difficulty of the task by introducing an artificial ground plane carrying the log. The agent first learns to grasp a log that is placed directly beneath the grapple on the red area shown in the image. The distance between the log and the grapple then increases as the agent progresses through the curriculum. As is depicted in the image, the log is moved to the side of the load bunk, marked in blue, after which the artificial plane is incrementally lowered towards the ground. By the final lesson, the agent learns the original target task by learning a policy that has incorporated knowledge transferred from the previous subtasks. Next, I will walk you through some of the most important results. To the left, we can see the evolution of the average episodic return obtained during the training process of our non-energy optimized policies. Overall, the training process is stable, and the approximately constant return during the first 5 million training steps shown in the plot correspond to the 30% success rate required for the agent to move through the curriculum. The performance evaluation of the final policy is based primarily on the grasping success rate over 1,000 consecutive episodes. Success, in this case, is recorded when the log is lifted from the ground, secured within closed grapple clause. Using this definition, our best policy achieves a 97% success rate, which is very high in this context. This policy is referred to as Policy A. Including energy optimization in the reward function, we learn 3 independent policies that achieve success rates of 81 to 93% in the given training time. These are referred to as Policy B, C, and D. With these policies, we are able to achieve a significant reduction in the total energy consumed during each boom cycle. Compared to Policy A, the energy is reduced by 61 to 78%. Here we can see the distribution of the total energy consumption over successful episodes in our evaluation for Policy A, B, C, and D, respectively. As we can see, the bulk of the distribution for Policy A, illustrated in blue, is concentrated at significantly higher energy levels than the other policies. It should also be noted that the increase in cycle time for the energy-optimized policies only amounted between 11 and 36% compared to Policy A, which is marginal in this context, and especially in relation to the energy reduction levels obtained. The absolute cycle times are around 4 seconds, which is comparable to what is achieved by human operators. So how does this affect the policies in practice? Here we can see the difference between Policy A and Policy B in action. Policy B, shown to the right, is learned using the reward function including an energy optimization goal. Note, for example, the overall smoother motion of the crane, which can be observed through the significant reduction in the grapple oscillations of Policy B compared to Policy A. Another interesting thing to note is the use of the grapple oscillations in the grasping process, shown by Policy A. This is actually something mainly seen in experienced human operators, so that was especially interesting to see in our autonomous crane. Let me now make an additional note regarding the crane behavior. Due to the redundant kinematical structure of the crane, successful grasping poses can be reached from an infinite number of crane configurations, and we can see that the 2 policies shown here favor very different solutions. Policy A uses the telescope Q4 a lot more than Policy B, which instead relies on the inner boom Q2 to reach the grasping pose. Human operators are actually instructed to use the telescope as much as possible, as this is considered optimal maneuver over entire boom cycles, when we also return the log to the load bank, which is not considered here. It is likely that we would see this behavior in the energy optimized policies if the energy consumption was optimized over the entire boom cycle during training. Next, we illustrate these energy reduction effects a bit more in detail. The most prominent effect can be observed in the overall smoother trajectory profiles of the energy optimized policies compared to the non-energy optimized policies. To the left, you can see the boom tip speed profiles over 5 different boom cycles for policy A, marked with solid lines, and policy B, marked with the dashed lines. So as we can see, the speed is generally lower and the speed profile is smoother for policy B, the energy optimized policy. To the right, we show the corresponding acceleration profiles during one of these boom cycles. Note that using policy B results in significantly less jerk than using policy A, especially at the point of grasping, which occurs around the 2.5 second mark. This result is encouraging, as jerkiness often poses a particular challenge in robotic automation. As a final part of this presentation, I will briefly discuss the robustness of our final policies. Training is carried out in an environment where the vehicle is static. To evaluate the policy robustness, which can infer the potential for transfer between simulation and reality, we evaluate the policy performance using a dynamic vehicle, essentially adding flexibility in the tire and terrain interaction. This forces the policy to handle crane oscillations not encountered during training. Our policies show promising robustness to these increased oscillations. Policy A maintains 83% of its original success rate, whereas policy B, C, and D maintain 33, 53, and 42% respectively. It is evident that the sensitivity is highly dependent on the specific link activation found by each policy. For example, small unforeseen oscillations can lead to policy B hitting the load bank with a grapple, as it tends to lower the inner boom early in the boom cycle compared to other policies. Moreover, we have made some additional sensitivity evaluations as well, for example related to the policy robustness to inclined terrains and uncertainty in crane mass. Details can be found in the paper, but overall the results indicate some generalizability and exhibit encouraging robustness to these variations, while also showcasing the need for training in more unstructured environments. To conclude and summarize, in this work we have demonstrated that deep reinforcement learning control can be successfully applied to automate the log grasping motion of forestry crane manipulators in a simulated environment, and that it's possible to learn successful actuator-based control policies for energy-efficient log grasping. We have demonstrated that curriculum learning can be used to solve the sparse reward log grasping problem. This approach removes the need for conventional trajectory planning and extensive reward shaping. By including an energy optimization goal in the reward function, it's possible to achieve significant energy reduction while maintaining high success rates. Our best control policy reaches a grasping success rate of 97%. Energy-optimized policies generate smoother speed and acceleration profiles, resulting in significantly reduced grapple oscillations compared to our non-energy optimized policies. Robustness analysis show encouraging policy robustness to environmental disturbances and uncertainties, but also showcase the need for training in more unstructured environments. Although a lot of work remains, this is a first step for research focusing on reinforcement learning control of forestry machines, which are heavy, dynamically complex vehicles operating and performing manipulation tasks in unstructured environments. With that, I want to thank you so much for listening. Feel free to contact us if you have any questions or want to discuss future research related to this area. Thank you.